We're going to talk about the mean value theorem today, chapter 5, lesson 2, how that relates. The mean value theorem is something that applies only to differentiable functions. So you got to make sure that what you're working with is differentiable. So that means no corners, no cusps, no vertical tangents, only to differentiable functions on a closed interval. So some of those are trick questions, especially on the AP exam, is they will say, can you, use the mean value theorem here? And you have to, it's not differentiable. So you have to say, no, it's not differentiable. I can't use the mean value theorem. Or the interval will be open. And you say, no, I can't use it because the interval is open. It has to be a differentiable function on a closed interval. And so what the mean value theorem does is it guarantees the equality, where two things are equal, of the secant slope from end to end Okay, it's the equality of the secant slope from A to B to the tangent slope at point C. Okay, the equality, it guarantees the equality of the secant slope from A to B to the tangent slope at point C. So that in the formula is f of b minus f of a over b minus a. That is the secant slope. And that guarantees that it must be equal to the tangent slope at point C. That is the statement of the mean value theorem. Those two things will be equal. And so visually, if you take any function, say like this, that's a function. It passes the vertical line test. And if you call the beginning of the closed interval A and the end of the closed interval B, and if you find the secant slope that connects A to B, so like this, if you figure out that secant slope, it guarantees that at least one C, if not more than one C, will have that same parallel slope. So maybe it's right here. Oops, that doesn't look so good. Maybe it's right there. Maybe that has parallel slope. So that's the first C. And maybe right about here it has parallel slope, and that's the second C. And maybe this one also has parallel slope, so that's the third C. And then C4 and C5. There doesn't have to be multiple, there just has to be at least one. So this one, the one I drew, has 6 of them. But what the mean value theorem guarantees is that it guarantees the equality at least once, if not more than once. There's at least a C one time. That will work, and there might be more than that. And so you'll be given some equations to prove that on. Okay, so prove the MVT holds for the following function: x to the 5th minus 5x to the 4th plus 5x to the 3rd plus 20 on the closed interval 1 to 2. So just for an example. So the requirements are that it's differentiable, which it is. X to the 5th is differentiable. And the requirements are that it's a closed interval, which it is. And so the equality of the secant slope and the tangent slope must be true. And so we're going to figure out the secant slope. The secant will be f of 2 minus f of 1 over 2 minus 1. And the tangent slope will be 5x to the 4th minus 20x to the 3rd plus 15x to the 2nd. And so you'll have to work out the secant slope. You'll have to work out what f of 2 is, and you'll have to work out what f of 1 is, and then come up with the answer. So f of 2 is going to be 32 minus, let's see, 80 plus 40 plus 20. Did I do all my math right on that? 3 to the 5th, 5 times 16. I think I did all that right. Minus f of 1, so minus 1 plus 5 minus 5 minus 20, all over 1. So let's see the fastest way. 20s cancel out, 5s cancel out. So 32 minus 40, negative 8, minus, I get negative 9. I'm doing that all in my head, so I hope that's right. And so what the mean value theorem says is because the function was differentiable and because you have a closed interval, then you have to be able to solve 5x to the 4th minus 20x cubed plus 15x squared equals negative 9. That should be solvable. Now you can use your calculator to solve that. So I'd grab out my graph, I would graph this equation, I would find the intersection points. And there's guaranteed a solution that fits that problem within the interval. All right, so grab out your calculators and let's check it. All right, when we see that there's 2 intersection spots. Okay, so there's an x1 and an x2. All right, and so you said 2 point what? 8.9 what? Just 2.89? Yeah, it's got to go to 3 decimal places. We always got to go to 3, 5.25. So that's what I get. 2.885. All right. So which one is the one we're looking for? Because remember, we have to be between, yeah, there's 2 answers, but we have to be between the interval of 1 and 2. So it's only this one. Okay, that's the only one that's within the interval from 1 to 2. And so even though you might get multiple answers, you only take the one that's within the interval. All right, the second part of your homework is going to deal with another theorem, which has to do with extreme behavior. All right, so the second half of our homework. The EBT, the extreme behavior theorem. All right, if a function changes nature, that's not what I want to say. I want to say if the slope of a function changes nature in between critical points, then the behavior changes. All right, so in order to understand the extreme behavior theorem, we have to know what critical points are. All right, so critical points, I'm going to put a star by it. The definition of a critical point, okay, comes from setting the first derivative f prime equal to 0 and undefined. Okay, the result of that, when you set the derivative equal to 0 and undefined, then you have what's called a critical point. Then you check between critical points. And last year when we were learning about this, we made charts. We made first derivative charts. So this is where we're really going to start getting back into some of the calculus we were doing from last year. I'm going to take that same exact function that we were just working on. So it's x to the 5th minus 5x to the 4th plus 5x to the 3rd plus 20. And I want to apply the extreme behavior function. So what I want to do is find the critical points of this function. We know it's differentiable and continuous because it's a kintic function, but we want to know what its critical points are. So you find the first derivative again, so 5x to the 4th minus 20x to the 3rd plus 15x squared. That is the derivative. We want to set this equal to both 0 and undefined. So we'll take 5x to the 4th minus 20x cubed plus 15x squared, and we'll check if it's ever equal to 0. And it's sort of a redundant. We know that it's because it's a polynomial, it will never be equal to undefined, but it's a good habit for us to practice that. So that won't produce any solutions, but the polynomial will. When I take out 5x squared out of that polynomial, I'm left with x squared minus 4x plus 3. I should not need a calculator to determine that because it's easily factorable. So we're going to have x minus 3 and x minus 1. So this function has 3 critical points. The critical points are 0, 3, and 1. And now what we want to do is look for a change in the behavior of the derivative, the behavior of the slope. And so we are going to have the intervals, and we're going to have the nature of f prime. You remember these from last year, making these charts? So we'll have an interval that's less than 0. We'll have an interval between the critical points of 0 and 1. We'll have an interval between the critical point of 1 and 3. And we'll have an interval greater than 3. And what we want to do is we want to check what the nature of the derivative is within each of those intervals by just selecting a number, a value that falls within the interval and testing our derivative. All right, so Tom, pick me a number that is in the interval less than 0. -1. All right, so we are going to take -1 and we're going to put it into those 3 spots. So when we put -1 into 5x squared, what nature do we get? When I put it just right here, when I put -1 in there, I get a positive number, right? What about x minus 3? A negative number. What about x minus 1? Okay, and so we're going to have a positive on the outside, 2 negatives on the inside. So the overall nature is a positive, which means that the behavior is increasing in its slope is positive, and so the original function is increasing. All right, so Yiting, pick me something in the second interval between 0 and 1. 0.5. Okay, put it into f of x squared. That gives you a positive. What about x minus 3? Negative. What about x minus 1? All right, so what's our overall? Okay, positive. So is there a change? So no change, which means there's no change in behavior. All right, between 1 and 3? 2, okay. What about the values? We're going to have positive on the outside. All right, so the overall nature is going to be a negative. So there's a change now. And so that means that x equals 1 is going to be, there's going to be a change in behavior because it's changing from a positive sloping nature to a negative sloping nature. And so x is 1 is a max when something changes from a positive slope to a negative slope. And then x greater than 3, that will give me a positive value again, which is another change. And so x is 3 is the min. And so our function, the behavior, is decreasing on 3 intervals. No, excuse me, decreasing on 1 interval. It's only decreasing between 1 and 3. It is increasing on 3 intervals. So it's increasing on the interval x less than 0, 0 to 1, and x greater than 3. Is it increasing or decreasing at 0? What about 0 itself? Okay, it's neither. It's not increasing or decreasing. Nothing's happening at 0. There's a name for that we'll talk about in a couple days. But does anybody remember that? Okay, you'll recognize it as soon as you see it when we do it in a couple days. It's called a point of inflection. Okay, but we'll talk about that later. So, yeah. But for now, we're just looking in the first derivative, and we're looking for our behaviors to change around there. Okay?